Hey guys, welcome to part 6 in this Bitcoin Cash wallet tutorial. In this video we're gonna implement the withdraw function that we created on our wallet module so that we can perform a withdrawal to the address and in the amount that the user wishes. By the end of this video we will be able to actually create and broadcast valid transactions from our wallet and send real money over the Bitcoin Cash network. So that's it for the intro, and let's jump right into it. So first of all, I'm going to open here where we left off on the previous video. As we can see, we implemented the get balance function, which is already giving us the real balance on our wallet. If I open the wallet again, we can see that we have 10,000 satoshis, which are ready to be spent. Now, before actually implementing the withdraw function, we need to talk a little bit about how funds are actually stored in the Bitcoin Cash network. By the looks on our previous video, it seems to be the case that an address has a balance, so it would seem natural to just want to spend a little bit of that balance if we want to do a transaction. However, in the Bitcoin Cash network, funds are not stored like that at all. There is no such concept as an explicit balance existing in an address. What actually exists is unspent outputs. The short term for unspent outputs is UTXO, which is what this endpoint here is for. In reality, the Bitcoin Cash network only stores outputs explicitly. That means that every time that you create a transaction, you're really doing nothing but consuming or spending outputs and creating new ones. So when you send money to an address, you're not actually increasing the balance of that address explicitly anywhere. What you're doing is you're just creating an output which sends a certain amount of satoshis to that address. But you could in fact send many outputs to the same address in the same transaction. The net result would be that you're incrementing the balance, so to say, on that address for an amount which is equal to the sum of all the outputs. But if you really want to spend that money, you necessarily need to recover all those outputs and spend them somewhat independently. You can spend them all in the same transactions, but you need to prove ownership of each UTXO or unspent output independently. So in order to actually start building a transaction, the first step that we need to do is we need to ask the network to provide us with all the existing non-spent outputs that exist for our address. And that's exactly what this endpoint exists for. So the first thing I'm going to do is I'm going to click try it out again. I'm going to click execute. And here we can see how when we do a get request on the address UTXO endpoint providing a given address, what we get here is actually an array. In this case, this array has a lot of elements in it. Each one of these elements is an unspent output. If you look carefully into each one of these, what they have here, they have a lot of properties, but the most important ones are the TXID, which is a reference to the transaction that created this output. Right below it, we have the vout property, which essentially tells us out of all the outputs that might have been created in this specific transaction, which one does this UTXO actually reference. So if we have a transaction like the one we have here with EED7 as an ID, etc., that transaction has a lot of outputs. In fact, we're going to see those right now. I'm just going to open this transaction on the Explorer. as we can see, this transaction has a lot of outputs, but the one specifically that we are seeing right now, which has not yet been spent on the network, is the one with the index 1. Since the indexing is 0 based, that means that we're actually looking at this output. And the first thing we're going to do then to actually implement the withdraw function in our code is we're going to get all the UTXOs which exist for our deposit address. So I'm going to copy this into our withdraw function. Again, I need to do a fetch here. And instead of using the address that is provided by the API, we're going to use our own get deposit address. With the result of this request, we need to again check if there was any problem with the response, the same way we did it here with the balance. In fact, I can copy most of this and just change the error message. As a response, in this case, as the result, the JSON object, which is returned by the API in this case, is an array of UTXOs. So the first thing I'm going to do here is just log to the console what this array is. So let's refresh our page. And let's click on the withdrawal function. Here we're seeing the object promise because for the same reason that we got it on the previous video, the withdraw function used to return just a string, but now it's returning the promise. So we need to do something about that, but we're going to do that later. Let's take a look first at the console log. Here we can see that for our deposit address, there is only one UTXO. The reason for that is essentially that we just did a single transaction sending money to our deposit address, which has a single output, which is the one we created on the previous video. So if we take a look at the UTXO object, here we can see the TXID that we actually generated on the previous video. And the vout is essentially the index of the output that we're seeing right now. If we take a look at the amount, we can see that the amount is this amount here is expressed in BCH, but this is exactly 10,000 satoshis, as we can see down here, which is the amount that we sent on our previous video and that we have as a balance. So now that we have the UTXO, one thing that is interesting to know, like I said before, the blockchain doesn't store explicitly the concept of a balance for an address. There's no such thing within the internals of the network. In fact, when we call the function address details on the API and we get the property balance satoshis, for example, rest.bitcoin.com is actually computing this for us in the backend. So now we're going to do something similar, which is compute our balance based on our UTXOs. And we can do that because the balance itself is defined as the sum of all the satoshis in each of our UTXOs. So in order to do that, I'm going to create a variable balance. And the result of this is going to be just reducing over the UTXOs array. If you've ever used the reduce function before, you know that it essentially performs a function on every element of the array and keeps an accumulator of the end result. So the function we need to pass to reduce, first of all, is the accumulator value, and the next one is the actual element that we're processing. So here we're going to return the accumulator, which is the partial result, and for each UTXO we're also going to get the satoshis that we can see are defined here. We also need to provide the reduce function with the start value for the reduce function, and when using the plus operation, we just add a 0, and that essentially tells us to get the sum over all the satoshis on each UTXO in this array. So now we can log to the console this balance and make sure that we're actually getting the same balance that we were getting on our getBalance function. I need to perform a withdrawal. Okay, and here we can see balance 10,000. So this is working just fine. Now that we have the UTXOs and we know the balance that we're computing ourselves instead of depending on Bitcoin.com to compute, now what we actually need to do is we need to create a transaction. So Bitcore has an object called transaction for this, which is really handy, and that's what we'll be using. When we're creating a transaction, like I said before, every transaction on the Bitcoin Cash network is essentially just consuming a set of unspent outputs and producing new ones. So the way we do this is we first tell the transaction to consume the UTXOs that we have fetched from the network. And the next thing that we want to do is we want to tell it what the outputs are. So first of all, we're going to add one output which goes to the address that we received as an argument to the withdraw function. And the amount is just going to be the value that we received here as well. I'm going to change this name value for the name amount. Again, this is an amount in Satoshis. And before moving forward, it's important to understand that the amount that we're spending might be a lot smaller than our address's full balance. And like I said, there's no such thing as only spending an output partially. If you spend the output, you spend it completely. So if you have 10,000 Satoshis as a balance, you cannot just send 1,000 Satoshis and keep the rest in the same UTXO. The way this is handled in the Bitcoin Cash network is whenever you're spending an amount which is greater than the one that you want to withdraw, you create a new output which sends back all the change, the leftover money to yourself. So what that means is we want to send back to ourselves. So we want to get our deposit address. And the amount that we're going to send is essentially our full balance minus the amount that we received. Now there's a couple things that are wrong here, and I'm going to fix them one by one. First of all, this keyword here won't really work because by the time that this function gets executed, the this member is not really the wallet object anymore. So the way we fix that is we're going to store the this value at the time the withdraw function is executing into a variable self, and then we can use that one down here to make sure that it's still referring to the wallet. Now another thing that's wrong here is that if we actually send the balance minus the amount to ourselves, that means that we're in total we're not leaving any fee for the miners. This transaction, as displayed right now, would be a zero fee transaction. Now, in the Bitcoin Cash network, such transactions are never allowed. There's always a minimum fee that you need to provide for the miner that's going to include your transaction in a block. In the way to actually adding fees to your transaction is the Bitcore transaction object actually has some functionality for doing this automatically for you, but we're going to implement it ourselves to see how it happens. The way this works is the fee is defined as the leftover money in the transaction. That means that if you're consuming 10,000 Satoshis as an input, that means you have a UTXO for 10,000 Satoshis, and the sum of all your outputs is, for example, 9,500 Satoshis. That means that you're leaving 500 Satoshis as a fee for the miner. There's nowhere in the transaction where the fee is written down explicitly. It's simply defined as the difference between the inputs and the outputs. So I'm gonna write here a fixed fee. We're going to change this later, but this is just to see how the fee plays part in the creation of the outputs. So I'm going to create a variable fee with a value of 250, and since we want to send the amount that the user provided to the address that the user provided, the fee needs to come off from our change, because otherwise we would be sending less amount than we actually wanted to. So if we take a look now, the whole input to our transaction is the amount balance, which in this case is 10,000. We're sending amount to this address, and then we're subtracting amount from the balance to send that to ourselves. But we also need to subtract the fee, since that is what the miner is going to receive as a reward for mining this transaction. The last thing that we need to do here is we need to actually prove that we own the UTXOs that we're trying to spend. Like we mentioned on the previous video, the way we do this is we need to create a digital signature. We're not going to do that ourselves. Bitcore does this for us. The low-level details are in the library, but what we actually need to do here is we need to sign the transaction with our own private key. So that's the way this works. Here we don't really need the text representation of the private key, but rather the private key object, which we already have. And by this point, after the signature, now this has become a valid transaction and is ready to be broadcasted to the network. In order to actually do that, we create what's called a raw transaction, which is essentially just an array of bytes which holds the same information as our transaction object. Here we're going to call a function called checked serialize. What this function does is it grabs our transaction object and it produces a raw transaction from it. But first it makes sure that everything is okay. If there's been any problem, if you forgot to sign it, for example, that function will fail. So I actually have a typo here I need to fix first. Serialize, that looks good. And instead of actually broadcasting this, we're gonna return it first so that we can see it in the UI, and I'll show you guys how this looks. To actually make this show up in the UI, we need to fix this first, because the withdrawal function was originally returning a string, whereas now we're actually returning a promise. So we need to do something similar to what we did with the balance, and we need to add a then statement here. This statement receives a TXID and then also performs an alert like it did before. I'm also going to do a refresh of the page right after a transaction, so that we make sure that we can see the updated balance right away. Before testing this out, I'm gonna do a little bit of cleanup here to the function arguments. So the first one is just a string. I'm just gonna make sure it doesn't have any white space at the beginning or at the end. And the second one, it's a number. So I need to make sure that this is actually passed to the withdrawal function as a number and not as a string. For that, I added this unary plus sign, which makes sure that this value, which is actually a string, gets converted into a number. There's just one more thing here that's missing. That is to actually make sure that we handle any network errors the same way that we did with the getBalance function. I could just copy paste this code here, but since this function is exactly the same in both cases, I'm actually gonna factor this out. I'm gonna call this handle error here as well, and I'm gonna define that function down here. And that's it. So let's see how that raw transaction looks like. I'm going to refresh the page now. I'm going to add a real address. I'm going to add an amount and click on withdraw. Okay, so here what we're seeing is not a real transaction ID, but just a raw transaction which we're returning from the withdraw method. So this is just like a really long a bunch of data in hex, in hexadecimal. This is exactly the data that we need to broadcast to the network. So for that, we have this endpoint here called raw transactions / send raw transaction. This is part of the rest.bitcoin.com REST API. So if I open this one up, here I can see exactly what is the request URL that I need to use. So I'm going to copy the prefix without the example transaction. And we're actually going to put this here. We need to do a fetch here to exactly this address. Here we need to add at the end our raw transaction in hexadecimal, the one that we're just looking. So instead of just one thing first, this fetch request is actually supposed to be a post request, unlike the previous ones that we have used that were get requests. That means that we need to tell this fetch function to actually perform a post instead of a get. This is the syntax for doing that. Now, right after doing this fetch, we need to do the same thing that we do on all the others, which is to actually handle the case where the request can fail. So in order to actually handle that, what I'm going to do is I'm going to copy this code that we had before, and here I'm going to say broadcasting transaction failed, if it is the case that the transaction has failed. Now, there's also another difference in this case, which is that the response that we get from this endpoint, if we look in the API, is actually just a string. It's not really a JSON object like in the other cases. In this case, with the fetch API, what we actually need to use here instead of the .json function is the .text function, which doesn't really parse the body of the request and just returns it like a string. And in this case, there's an important distinction here. This send raw transaction endpoint actually returns us a text which can be one of two things. It can either be a transaction ID if it was the case that the transaction was successfully broadcasted, or it can also be a textual error message saying what went wrong. So what we need here is a way to making sure whether that text variable contains a valid TXID or whether it contains an error message. So the way we're going to do that is we're going to use a regular expression saying if the text that we have there matches, I'm going to use a regular expression for this here, which essentially just checks whether this is a valid TXID. So in order to check that, we're going to use a expression to check whether it's a string of characters from 0 to 9, characters from A to F, or A to F in uppercase. And we need to have exactly 64 of these hexadecimal characters, since that is the length of a transaction in transaction ID in hexa. The reason for that is essentially that the transaction ID is nothing other than a SHA-256 computation, which means that the output is 256 bits, which boils down to 64 hexadecimal characters. So this expression I just wrote down here tests whether the response that we get back from the REST API is actually a valid transaction. So if the result of that match is a null, that means that the text that we have here actually does not contain a valid transaction ID. So instead, what we need to do here is we need to throw a new error. We can actually just copy this message, but we also have a difference, which is that in this case we actually know exactly what went wrong, so we can say exactly what the error was by using the text here. And otherwise we just return the text, which is a valid transaction ID. So now everything looks ready and set to test this out. So I'm gonna come here to our wallet, I'm gonna refresh the page, and I'm gonna use our valid address, and I'm gonna put in the amount of 5,000 satoshis. And there we go. We just created and broadcasted our first fully valid Bitcoin Cash transaction from our wallet. So now the page will get refreshed, and here we can see the balance, which is 4,750 satoshis. The reason for that is that essentially we just sent out 5,000 satoshis to a different address, and the change to us is equal to the original balance minus the 5,000 minus the fee, which we hard-coded as a 250 value. We can also see that transaction on an Explorer. We're going to do that now. So right here is the transaction that our wallet created and broadcasted successfully. Here we can see the 5,000 satoshis going to the first address that we defined, and 4,750 satoshis which come back to our own deposit address as a change. So what we've just completed is the first withdrawal flow for our wallet. This is a very basic flow which has a hard-coded fee, and it always has a change address. It also has a change output which comes back to our deposit address. Now there are many cases in which this very logic that we wrote down here doesn't fully work. Like for example, if you spend the full amount instead of just a fraction of all your balance. So on the next video, we're actually gonna make sure that this logic we wrote here is airtight and doesn't have any of all these border cases that would make this transaction fail. So that's it for this video, and see you next on part number 7.